Okay, so in this talk, I'm going to tell you something about variety evasive subspace families, which are objects that we introduced in this paper at CCC. And let's start with the introduction. So one motivation for our work is the problem of polynomial identity testing, or PIT. It takes as an input a multivariate polynomial, P in variables x1 through xn, that is computed in some computational model like arithmetic circuit or arithmetic formula. And our goal is to decide whether or not P is identically 0. And we want to do this in a deterministic way because there's already an efficient randomized algorithm. And one special kind of PIT algorithm is what we call black box PIT algorithms. And these are algorithms that can evaluate polynomial P at given points as an oracle, but they're not allowed to look into the structure of P. And it's well known that deterministic black box PIT algorithms is equivalent. Designing such algorithms is equivalent to designing what we call hitting sets for polynomials. And here is the definition of hitting set. So we say S is a hitting set for family C of polynomials if for any non-zero polynomial P in the family C, the set S contains the evaluation point alpha such that the evaluation of P at alpha is non-zero. So this is definition, and we can also look at the property, hitting set property in a geometrical way, namely for each polynomial P, non-zero polynomial P, there is a corresponding hypersurface of the n-dimensional vector space F to the n, and this hypersurface is simply the set of all the roots of the polynomial P. And then S is a hitting set for family C of polynomials if and only if for every non-zero polynomial P, the set S contains at least one point that is not in the corresponding hypersurface HP. Or we say S has at least one point that evades the hypersurface HP. And we can consider a generalization of this property to higher dimensions or codimensions. Note that hypersurfaces are also varieties of codimension 1, and points that we choose are affine zero subspaces or subspaces of dimension 0. And we can consider the more general problem of constructing a collection of k subspaces or subspaces of dimension k that evade general varieties. And this leads to a notion of what we call variety evasive subspace families. And this is the formal definition. Suppose C is a family of subvarieties of f to the n of dimension r. And for simplicity, let's assume f is an algebraic closed field. And let S be a finite collection of affine k subspaces or subspaces of dimension k. And we say the collection S is C evasive if for any variety V in C, S contains at least one k subspace such that the following condition is satisfied. If k plus r is less than n, then we want W to be disjoint from the variety V. And if k plus r is greater than or equal to n, then we want the dimension of the intersection of v and w to be bounded by k plus r minus n. And note that this condition is satisfied by k subspace w in general position. And we can even formulate a stronger condition about than the C evasiveness. We define S to be C epsilon evasive if this condition holds not only for some W, but for all but the epsilon fraction of W in S. We may also consider a projective version of variety evasive subspace families. And this definition is just like before, except that we are working on an n-dimensional projective space. And the affine varieties are replaced by projective varieties, and affine subspaces are replaced by projective subspaces. And actually, in our paper, we mainly focus on the projective version, and the affine case can be easily reduced to the projective case by identifying the affine space f to the n with an open subset of p to the n, the projective n space, and noting that restricting to the open subset preserves the evasiveness. Variety evasive subspace families are also related to pseudo-M objects called lossless rank condensers. Here's the definition. Suppose F is a finite collection of linear maps from F to the N to F to the T, and we say F is an R epsilon lossless rank condenser if for every R subspace V, all but at most epsilon fraction of the linear maps in F preserve the dimension of V. And these objects have applications in PIT and pseudo-randomness, and there are explicit constructions for these objects. And their connection with variety evasive subspace families given as follows. A collection F of surjective linear maps is an R epsilon lossless rank condenser if and only if a certain subspace family is C epsilon evasive, where we choose C to be the family of R-1 subspaces of the n-dimensional projective space. So this means variety evasive subspace families generalize the problem of the notion of lossless rank condensers in a special case that variety are subspaces, they are exactly lossless rank condensers. And they also generalize the problem of black box PIT when the varieties are hypersurface, as we have seen. So this problem simultaneously generalizes the two problems. Finally, variety evasive subspace family is also related to what we call a no-cell normalization lemma, which is a fundamental lemma in commutative algebra and algebra geometry. So there are different versions of this lemma. Here I state one of them. So suppose V is the projective subspace subvariety of P to the n of dimension R. And the lemma states that there exists a map from V to P to the R that is a so-called finite map. And moreover, one version of the lemma states that we can choose such a finite map so that it comes from a random linear map. And one natural question of this about this lemma is how to de-randomize it. It can be shown that de-randomizing a no-cell normalization lemma is equivalent to constructing explicit variety evasive subspace families. Specifically, suppose we have a C epsilon evasive subspace family, then we can use it to construct a collection of linear maps such that most of them would induce the finite map from the varieties in C to P to the R, where R is the dimension of the variety. And we can also go in the other direction. So this means the problem are basically equivalent. And I also want to remark that in the literature, there's also work in the computer science about no-cell normalization. In particular, the paper of Mumuli studied no-cell normalization, but that paper is kind of in a different setting. In his paper, the dimension of the ambient space is actually exponential, and the linear maps are specified in a very succinct way. So this is a kind of different setting compared to our setting. And Mumuli showed that de-randomizing and no-cell normalization in this setting is equivalent to a strong version of black box PIT against the so-called border complexity classes. Next, I'm going to talk about explicit constructions of variety evasive subspace families. In our paper, we focus on the construction for varieties of low degree. Here, the degree of a variety V is defined to be the number of intersections of V with a subspace in general position, whose codimension equals the dimension of V. And we focus on the family C and D, which is the family of varieties of whose degrees are bounded by D. And note that here I have not specified the dimension of the variety, only the degree. But in fact, it can show that it suffices to consider varieties of codimension exactly k plus 1. And if we can handle if we can handle varieties of codimension k+1, then we can also handle general varieties of arbitrary dimension. And so we may assume the codimension of V is exactly k+1. And also using argument of union bound, we could assume that the variety is an irreducible variety. So from now on, we may assume the variety has codimension k+1, is irreducible, and has degree at most d. Okay, so we first give a simple construction of variety evasive subspace families against low-degree varieties. First, consider the simple case where C consists of hypersurface. In this case, the problem is equivalent to PIT for low-degree polynomials. And using determinist sparse PIT, we could get the construction of size polynomial n plus d, n plus 1 plus d choose d. So when d is bounded, this gives the construction of polynomial size. And in general, for general varieties, our strategy is again reducing to the problem of PIT for low-degree polynomials. Now, but we need to associate with each variety a polynomial. So how do we get this polynomial? When a variety is a hypersurface, the polynomial is simply the polynomial that defines the hypersurface. And for general varieties, we need a notion of Chow forms, which was a notion in algebraic geometry introduced by Cayley, Chow, and Van der Waerden. Let me explain what a Chow form is. Suppose V is a variety of degree D and codimension k+1. Because codimension of V is greater than k, we know that the k subspace in general position is disjoint from V. However, there are some bad k subspaces that would intersect V, and the Chow form of V is a polynomial that defines exactly the set of these bad k subspaces. More specifically, we represent k subspace W by k+1 times n plus 1 matrix MW, whose k+1 rows specify the points that span the subspace W. And then Chow and Van der Waerden show that there is this polynomial RV in k+1 times n plus 1 variables, and the degree of this polynomial is k+1 times d, and the polynomial satisfies the following property. K subspace W intersects V if and only if the polynomial vanishes at the matrix MW. So in this sense, this means that the polynomial vanishes precisely at the set of k subspaces that intersect the variety V. And moreover, this polynomial RV is determined by V up to scalar, and we call the polynomial RV the Chow form of V, or more specifically the Chow form in state-field coordinates. And so the problem becomes hitting the Chow form of V, and this is the PIT problem. And because the degree of the Chow form is k+1 times d in k+1 times n plus 1 variables, we can use deterministic sparse PIT to give a construction of size polynomial in k+1 times n plus 1 plus d, choose k+1 times d. However, this only gives the construction of polynomial size when both the dimension k and the degree d are bounded. So it works only for varieties of a constant degree and constant dimension. There is also a dual version of the Chow form. Suppose instead of representing a k subspace by k+1 by n plus 1 matrix, we now represent it by n minus k by n plus 1 matrix, whose rows specify the linear equations that define the k subspace. In other words, we represent a subspace by its parity check matrix instead of generating matrix. Then the dual version of the Chow form vanish at precisely the set of matrices corresponding to the k subspaces that intersect the variety. And then similarly, we could use this dual version of the Chow form to give a construction of size that is polynomial in n minus k times n plus 1 plus d, choose n minus k times d. And this gives a construction of polynomial size, but only when the degree d and the codimension n minus k of the variety are both bounded. So now we have polynomial size constructions when d is bounded and either k or n minus k is bounded. However, this still does not address arbitrary k. So we can ask if there is a construction of polynomial size for arbitrary dimension k and bounded degree d. And note that when the degree d is 1, then this is the problem of constructing lossless round condensers, and we do have such constructions. So the question is whether or not we can extend to general bounded d. Now I give a construction, an improved construction that has polynomial size as long as the degree d is bounded, regardless of the dimension k. And this is achieved by solving the equivalent problem of de-randomizing Noether normalization lemma, which I mentioned before. It's about constructing a collection of linear maps such that most of these linear maps give valid finite maps from the variety V to a projective space. And in the following, let's define the span of V to be the smallest projective subspace containing V. Then it's a fact in algebraic geometry that if V is an irreducible variety of degree D, then the codimension of V in the span of V is at most D minus 1. And this fact will be used in a moment. And our idea is to use the two-step construction. So we first construct a finite map pi1, not on V, but on the span of V. And this can be achieved efficiently using explicit lossless round condensers because the span of V is a finite space. Its degree is 1. It's a projective space, and its degree is 1. And then we construct a finite map pi2 from the pi1 of V to a projective space. And this can also be solved efficiently because the codimension of pi1 of V in the span of V, in the projective space is small. The codimension is bounded by d minus 1, and so we can use our dual construction on the previous slide to solve this problem. And we also need the fact that the composition of finite maps is also a finite map. So composing pi1 and pi2 gives the desired finite map. Using this idea, we give a construction of polynomial size for arbitrary k and the bounded d. And in fact, if the dimension k is a subpolynomial in N, we can even handle slightly superconstant d. Although in our paper we did not achieve this, but this will appear in the full version of our paper. And the next thing I want to talk about is the lower bound for the minimum size of variety evasive subspace families. In our paper, we prove this theorem. And suppose S is a projective K-subspace family that is evasive against the family of the family C and DK, which denotes the family of projective varieties of degree at most D and the codimension K plus 1. And then we show that the size of S must satisfy this lower bound. And I want to note that this lower bound is optimal and can be matched by non-explicit constructions. And note that here the lower bound basically says that when D is small, it says that the size must be about at least about n to the D. So this shows that the assumption that D is a constant is necessary for variety evasive subspace family to have a polynomial size. And one nice thing is that when the degree D equals 1, then this lower bound is also matched by explicit constructions, particularly by explicit lossless round condensers. And this also shows that the existing analysis of explicit lossless round condensers is actually optimal. And next I'm going to briefly sketch the proof of this lower bound. So it uses a dimension counting argument. The first step is to give a variety structure to the set C and CDK. So it can be shown that the set C and dk after adding some extra points is actually a projective variety, and this is called a Chow variety in the literature of algebra geometry. And the way to implement a variety structure uses the Chow form that we mentioned before. And then it can also be shown that the size of S is has to be greater than the dimension of this Chow variety. Um, the intuition here is that if the size of S is too small, then we can find an adversary variety in the set C and dk that evade every case subspace in S, but this would contradict the assumption that S is a variety evasive subspace family. So the size of S has to be at least the dimension of the Chow variety, and one other thing is that the dimension of the Chow variety has been completely determined in the literature of algebra geometry. So we plug in the value of the Chow variety, and this shows the lower bound. And about applications, we believe variety evasive subspace families are natural objects, and we expect they can find applications. Here, let me list two applications we know. One is the de-randomization of the nose normalization lemma. As I said before, this is equivalent to constructing variety evasive subspace families. So our results translates into the randomization of normalization lemma. And another application is deterministic PIT for depth 4 circuits with bounded top fine-in and bottom fine-ins. So depth 4 arithmetic circuits are important because PIT for depth 4 circuits, a strong enough PIT for depth 4 circuits actually imply PIT for general arithmetic circuits. And very recently, Duta Dividi Saxena gave a quasi-polynomial time algorithm for this class, and Limaye, Srinivasan, and Travanas in a very recent exciting breakthrough gave a sub-experimental time algorithm that works for PIT algorithm that works for all bounded depth circuits. And we follow a more traditional approach. We look at the 2014 paper by Gupta, who gave a PIT algorithm for so-called sigma k pi sigma pi r circuits that are not in the so-called Sylvester-Gallai configuration. So in his paper, so he gave a PIT algorithm for this, and he divided the class of depth 4 circuits is topology top and bottom fine into two classes. One is those in the Silva-Scala configuration, and one class is those that consists of those that are not in the Silva-Scala configuration. And those that are not in the Silva-Scala configuration are the easier one. And he gave a polynomial time deterministic PIT algorithm for this class. And we observed that his proof, all he needed is just a construction of subspace families that are evasive against certain varieties of bounded degree. So we plug in our construction of variety evasive subspace families and obtain a simpler proof, and also improve the time complexity. More specifically, we improve time complexity from about n to the poly r to the k squared to n to the o r k, r to the k. Okay, so these are the applications, and finally, I want to give you some open problems and future directions that I found interesting. One problem is improving our explicit construction of variety evasive subspace families. In our construction, the size is basically n to the O of d square, at least when d is of little o of n. But the optimal bound should be n to the O of d only. So one question is if one could close this gap. And also, if we only consider varieties of constant dimension, then actually the optimal bound is only polynomial size. But I do not know any sub-exponential size construction for that sub-exponential in the minimum of d and n. And another Direction is considering the explicit construction and proving lower bounds when we relax the condition of evading. And say we could allow the dimension of the intersection of v and w to be smaller than the dimension of v plus dimension of w minus n. Sorry, slightly greater than this bound. Or we could consider a setting where there's a gap between the dimension of variety of v and the codimension of w. And it should be easier to construct variety evasive subspace families if we relax it in this way. So are there better explicit constructions? And also, what kind of lower bounds can we show for such relaxations? And finally, last problem is, are there better constructions for other special families of varieties? We only consider varieties of small degree. So maybe there are some families of varieties that are interesting and defined in certain combinatorial way or computation theoretical way for which we could give better constructions. So that's the end of the talk. Thank you for your attention. And if you have questions, please feel free to email me. Thank you.